This is Viz 2320 Computing 2, and this is the third video in the Finding and Avoiding Bugs series. So in the previous two videos we're talking about how bugs are almost an inevitable part of writing computer code. We discussed the three main types of bugs you're going to come across, so syntax errors, identifier errors, and then logic errors. So syntax and identifier errors are generally relatively easy to find, and development environments like Spider will give you a good head start to find where they are, and therefore make it easier for you to remove them. Logic bugs are much harder to get rid of, and obviously the best thing to go and do is to avoid introducing them in the first place. So the second video talked about a whole bunch of ways you can try and avoid introducing logic bugs into your own code. So that includes things like having sensible names for variables and functions. It's a lot about writing well-structured functions that do just one thing, and that you can test in isolation. And the other bit then is about writing good documentation for code. So we talked about doc strings, which are for you or other programmers to know how to use your functions, and comments, which are about explaining how the function actually works. So this video then is going to be mainly about strategies to try and find logic bugs once you've actually got them there. Okay, so the very first thing is to try and locate where the error is actually coming from, and so that means being able to understand and work out what the error message is actually trying to tell you. So when Python hits an error and crashes out with the bug, then you're going to get something which looks a bit like this. And the way to read this is to start at the bottom. So the bottom line tells you that what exact type of error you've got, the actual error message. So in this case it's telling you have a value error, a math domain error. Now sometimes it's obvious exactly what's gone on, sometimes it's obvious if you know what the error messages tend to mean, and sometimes it's a bit too generic. So for example, an error that just says runtime error can be not very much help. But in this particular case, actually a math domain error. This comes about because the square root function is trying to calculate the square root of a negative number. Okay, so that's probably what's going wrong there. There's a good hint here. There's only one math function going on there, so it's probably the one that's at fault. Okay, so the line above that is telling you whereabouts that error was hit. So this is telling us it came about in line 12 of the find roots of our betterstrings.py in a function find roots. And then the line above that is telling us that it was the find roots function. It shows us how it was being called. So find roots x, y, and z. And the line above that tells us this happened in line 40 of our program. The line above that, eventually, if you have a lot of functions you've been calling through, then you're going to have a long list of different functions. But eventually you're going to get to something which looks like the line that starts exec file. And this is actually part of Spider. So this and the line directly above it are actually inside the Spider source code. And it's actually part of Spider, where you told it to go and run the script. And then that's right at the very top is the bit that basically says this is the code running. So you want to start looking at the bottom and work your way back up to trace through how the function was actually being called, and to try and work out whether it was a chain of functions you were expecting or whether it's done something unexpected there. So that's the first thing to go and do. Having done that, you've hopefully now identified a series of functions that you suspect might be a problem. So if these are well-written functions, then hopefully you can actually try and test them in isolation. And by testing them, what I'm saying is trying them with known inputs where you know the results, you know the inputs are good and you know the results what the results should be, but also trying them with some bad inputs to see whether or not you get the error messages you're seeing. So quite often you can work out what exactly went wrong because you can trigger the same error message again with a set of bad inputs, and that gives you a clue as to what's gone wrong and what's been happening. And obviously you can work your way back up through the function trace, testing each function in turn, trying to make sure you work out what's going wrong and understand what's happened. So one of the useful things is that if you run Python from a console like you do in Spider, so even if you press the play button or hit F5 in Spider, generally what it's using is the IPython console that you've got opened up there as well. And that Python interpreter that's running in that console will keep on running even though your program stopped with a bug. So that means you actually have accessible all of the functions that were defined in your program when you ran it. And so that makes it a bit easier to go and check the code and make sure it does what you expect. Okay, so if we zip over to our Python code, so this is the code we were looking at the end of the second video. So it calculates the calculates the roots of a quadratic equation. What we're going to do is I'm going to introduce a deliberate error in it to force it to stop. So all I'm going to do is 1 divided by 0, which obviously should give an undefined result, so it's going to cause it to fall over. So if we go and run this code, there we go, so it asks us for the 3 coefficients. So I can put down here 1, 2 and -3, because I know that works. Okay, and there we've had the 0 division error. And you can see it's come back and it's told us where that is. So if I just pull that up a bit, you can see more of the context. So there's the 0 error, the specific line that caused the problem, where it was in the code, and then because that's running in immediately in the top level of the script, there's no function calls or anything else there. Okay, so because this code has gone and stopped unexpectedly, but the console is still there and running, that means my functions still exist. So for example, I still have whoops, too many functions that start with get. Get user input. So I can try just running that on its own, and you see there it runs, and I can put in, say, numbers again, 1, 2 and -3, and I see what I get is 1, 2 and -3 coming back at me. So that's doing what I expected. It's asking me for some input and it's returning those 3 numbers, and I can check, for example, what happens if I give it some bad input. So 1, 2, -3, -4, -5. Okay, and you see it's picked it up and told me it needs exactly 3 coefficients. 1, A, 3. So it's coefficient number 2 couldn't be turned into an integer. Try again. Okay, so this looks like it's being really quite robust, and that function seems to work pretty well. Okay, so and again I could do something similar with find roots. Of course, actually in this case I know exactly what my error is, and it's the one I just introduced there, so we can get rid of it. But you get the idea. So when your code stops, you can try running those functions independently, make sure it returns what you were expecting it to get. You can then sort of manually walk yourself through the code and make sure everything's happening as you expected. Okay, so that's the second of our strategies to go and try. So having worked out where the actual problem seemed to be happening, to try and make sure that the functions around it appear to be working. So of course the chances are that one of those functions isn't working, otherwise you wouldn't have had an error there. So the next thing is to try and actually work out exactly why it's not working, how is it not working properly. So there are a couple of things you do at this point. You can put some traps in the code to try and force an immediate halt when you have some bad data. So this is making use of the assert statement, which I introduced in the last video. So this is particularly useful if you think that the problem is your function is falling over because it's getting some bad input from somewhere else in your program. So you can put some tests as you go back through your stack of functions you've called through, and try and work out where it's generated the bad data. Where did the bad data first originate from, by checking for that bad data with an assert statement and causing it to stop immediately. The other thing that you can do quite effectively is simply add some more extra output to your code to get it to print out extra values or extra intermediate results. So put lots of print statements in. You have to use this with a bit of caution, because if you have too many print statements flying around, then it can just get very distracting and it can be very hard to work out what's going on, especially if you have say a loop running which is going to run through a lot of iterations successfully before something goes wrong. It can be very, very hard to go and spot the one line where it's told you something's gone wrong in amongst thousands and thousands of lines of it doing what you were expecting it to go and do. So judicious use of print statements is probably to be recommended. Okay, so just to go back over the assert statement, since I'm going to assume that you know how to use print already. So assert basically is a statement that causes the program to stop with an error if some condition is not true. So it's particularly useful for debugging because it allows you to selectively test your assumptions you're going into a function or in the middle of a function, and then cause an immediate stop with a message that you can define if those assumptions are not correct. So the general syntax is then assert, and then some condition which is going to give you a Boolean value, and then a message which should be printed out along with the error if that Boolean value is not true. And what you get out of it is an assertion error, followed by whatever error message you put. Assert technically really is mainly a debugging tool. There are ways you can run Python that tell it to go and remove all of the assert statements from the code, because obviously testing for things does take some extra effort, so you don't want to have assert lines in that are not necessary. Okay, so we've actually got some assert statements already in our code. So on the find roots function, I put a couple of asserts in earlier. So the first one, I'm checking that my coefficients a, b and c are all in fact integers. What we see here then is that I'm using the isInstance function. So isInstance is one good way of checking. You can basically take two parameters. The first one is the variable you're checking, and the second one is a type. So in this case, int. So you can check whether or not a is an integer. There is one thing you need to be a little bit careful of. If I do isInstance, so if I do say isInstance 1.23 comma int, it'll tell me it's false. If I do isInst 1 comma float, it'll say it's false. That's all as you'd expect. What you might not expect is isInstance true an integer. So you say, well, true is a Boolean value, is not an integer. So when isInstance comes up and tells you the Boolean is an integer, then you might get a little bit confused. This is basically because internally a Boolean is an integer, where 0 is false and anything that's not 0 is true. When you ask is a true value an integer, it says, well, true is actually basically -1 or 1, and therefore it's an integer, and therefore that comes out to be true. But with that proviso, isInstance is a good way of checking whether things are the type of variable you expect them to be. So if any of these are not integers, then it's going to stop and say, oh no, non-integer coefficients. And the other thing I'm asserting is that a mustn't be equal to 0. So that would mean that this wasn't a quadratic equation. If there's no x squared term, it's not quadratic, and trying to apply the quadratic equation is not going to work because you end up with a division by 0, which would give you another error. So that would be, for example, a way of protecting yourself against the case where somebody puts in 0, someone has managed to call the find roots function with a equal to 0, because otherwise it would fall over in one of the lines further down where you would try doing a division by 2 times a, and that would fall over. Okay, so that's basically the use of assert to go and protect or work out whether or not the values you've got are what you were expecting them to be, and to stop with a more sensible error message rather than letting them go on and try and do calculations with impossible numbers. Okay, so that's a collection of ways of working out where the error is, what the error is doing, where exactly in your code the error is coming and how you got there, trying to check for bad inputs, trying to check that you know what's going on and look at the intermediate results. The final tool to talk about is using a debugger. So Debugger is basically a tool that runs a computer program in a way that means you can stop at any point, you can check the variables, you can sometimes even change the execution order, you can jump over a line, you can step through the code one line at a time, and so on. So Python comes with a built-in debugging module called PDB, for Python Debugger, which you can use in your code. So I put a reference at the bottom of this slide to the documentation for that, for using PDB. So Spider actually comes with at least some support for PDB built in. Doesn't do everything that doesn't support everything that PDB can do. And to be honest, in Spider 3.0 and onwards, it's been a little bit flaky. So occasionally it decides to go and fall over in slightly annoying ways, but it's still quite handy, and it's nice having it actually built into the development environment without having to change your code or anything. So what you can do is you can set breakpoints. So you can say stop and pause here. You can set conditional breakpoints, which basically says stop and pause here if something is true. You can look at variables, not in Spider, but if you're using PDB kind of in raw, then you can also in fact change variables on the fly. And in particular, you can step into subroutines or continue through them until they're returned. You can sort of dig in and work out exactly what's going on in your code. Okay, so just as a very quick demonstration of how you use the debugger in Spider, I won't try using it in kind of the manual mode of like documentation would show you. Instead, we'll just use the slightly more limited functionality that's built into Spider. So normally you'd run your program by clicking on the play button, the run file, or hitting F5. If instead you use the play pause button here, then this puts it into debug mode, or you can also hit Control F5 to do this. So if I do this, then it comes up and you see down the bottom here it's printed out something. It's showing me it's trying to run the first line, and it's giving me the PDB console prompt. I'm going to carry on pressing buttons on the toolbar, however. So working my way over, the next button says run the current line. The button after that basically runs the current line, but if that involves calling a function, it steps into the function and actually steps you through the function. The next button is to continue until you get to the end of the current block of code, so the point at which your function is going to return, basically. And then the final two buttons, this one says carry on running the code until you hit the next breakpoint or the code finishes, and the final button is basically give up and get out of the debugger immediately. So let's just step over this code then. Okay, so Spider's now managed to work out where we are and is now highlighting the line we're just about to run, and then run the next line, and then the next line. So the def lines, notice that, so def, if you remember, is actually saying create a label and identifier, in this case get user input, and then attach to it the Python code that follows it. So it doesn't actually do anything with the function itself at this point. It just simply makes a note of that code and attaches it to that label. And it's not till you get down here that you actually get into the code that executes the function. So now we're going to try and step into this function. This, I have to say now, is one of the things that Spider occasionally falls over on, and indeed it has done in this case. So what we'll do is we'll just carry on and continue, and I'll show you about how to run a breakpoint in the code, which is the other way of stopping the program inside a function. So we run through, and now it's asking us for the coefficient, so I'm just going to go and put some numbers in and let the code run through, and the code's now run through. So with the code not running, we can now go and tell it to go and put some breakpoints in. So what I want to do is I want to investigate what actually happens inside this find roots function. So what I'm going to do is going to put a breakpoint on this line here. So I can go to the debug menu, and I can do set clear breakpoint, like so. So now I can run the code again in the debugger, and there we see we've started the first line again, but rather than stepping through the code line by line by line, I'm just going to say carry on running. And so we're doing the get user input function, and that's running as normal. So I give it some user input, and now it's managed to stop at that line where it's about to calculate the kernel. Now if we look at the Variable Explorer window here over on the left, then what we should see is that we're starting to get the variables that we've got inside the function. Okay, so I've just told it now to step one line over. It's updated the Variable Explorer, so I've got A, B, C, which are my parameters, 1, 2 and -3. That's the A, B and C I passed in there. X, Y and Z also exist, and the reason X, Y and Z exist is because they're global variables. They're variables I've created at the script here, which are going to exist when I call this function. So if that's not clear, then have a look at the functions videos, probably functions 1 and 2. And then I've just calculated this kernel variable here. I can see that's taken a value of 16. These other variables that exist here, things like E and pi, that comes about with how I've imported some options I've set on Spider to import NumPy modules in automatically into my console. I'll show you how to set that setting when we look at the NumPy module in a future video. Okay, so we're going to carry on stepping through this code. So we see that first of all it says, well, is kernel less than 0? No. It's greater than 0. Is it equal to 0? No. So therefore we do this else. So now we can see it's going to calculate those roots. So there's root 1 and root 2. And now, for example, I could say carry on running until we get to the point at which we step out of this function. And it should let us out, and then we end up coming back to the end here, and now I'll just run through to the end because it's the end of the code. We could also change that breakpoint, so you can use F12 to set or clear breakpoints, and then you can use Shift F12 to set a conditional breakpoint. So let's set a conditional breakpoint there, and our condition is going to be that let's have C is less than 0 as our condition. Okay, so now we're going to run the code again in the debugger. Start it running. There it's in the first line. I'm going to say continue, and I'm going to do 1, 2, -3, and you see it's now stopped at the conditional breakpoint, and that's because my value for C was -3, so it was less than 1, and so it stopped. Okay, I know everything actually runs just fine, so we'll run all the way through, and there it's printed out the errors. And we can finish with the debugger. Okay, I could change that condition. So if I hit Shift F12, let's change the sense of that, and then we stop if C is greater than 0. Okay, and run the debugger again. Okay, there we are in the first line. Okay, now we're going to continue the code. 1, 2, -3, and now it didn't ever go and stop at the breakpoint because our C was less than 0, and I said only stop if C was greater than 0. So that's how you can use a breakpoint or a conditional breakpoint to go and stop your code when certain things are true. And then if I have no condition there, it becomes an ordinary breakpoint, and I can then clear it out the way. Okay, so that's a kind of very simple introduction to using the debugger. As I said, unfortunately under recent versions of Spider it's not as reliable as it was under Spider 2. So depending which version is installed on the cluster machines or which version you have on your laptop, you may find it easier or harder to actually get the thing to stop in functions as you'd want them to. Okay, so in summary, basically the whole of this video is about trying to figure out how logic errors can be tracked down. So logic errors they're hard to find, but it normally is possible. So the thing always to remember is that computers are in fact deterministic. They don't do things completely randomly, no matter what we joke about Windows. Of course, sometimes it's just hideously complicated, And I suppose, of course, strictly speaking, being a physicist, I should point out they do sometimes do things that are random, because so much of the central processing unit relies on quantum mechanics and solid state physics, and there's always a possibility that something unexpected happens. It's just very, 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 very unlikely. So we can basically say that computers are more or less deterministic. So strategies. First of all, identify where the error is. So that's about reading the error messages to work out exactly which line the error has happened on and how you got there. Testing to find out how the error was generated. So was it bad inputs? Was it a bad calculation? Did the function never work as you were expecting it to, or did it work most of the time and sometimes it didn't because something was wrong about the inputs? Trying to pin down the path that actually led to the error in the code, so using print and assert to work out how you got there, and then finally using a debugger to trace the execution, and that lets you actually go and really dig in at a very great level of detail into what's going on. And you can either use the debugger that's built into the code, or the other thing you can do, of course, is run it through on paper. And this kind of points again to my final point, really, which is keep notes of what you've checked, what's working, what hasn't worked. Don't be frightened to be writing things down on paper. It can be an awful lot more convenient to go and have a notepad beside you and make some notes as you go along of what you've checked and what you haven't checked, and that can help you stop going round in circles, going slightly bonkers staring at the screen. Okay, so I think that's probably enough for this video then.